Hello, welcome to Tea Leaves Programming. You're watching the series Haskell for Dilettantes. Today we are going to start working on homework number 2 in Joachim Breitner's CIS 194 class from fall of 2016. I believe fall 2016, yes. So what are we going to do here? We're going to continue what's called Haskell for Sokoban. We're going to start making the bones of a Sokoban game. So he's divided this up into a number of exercises, 4 in total. We're going to only do 3. The 4th exercise is make your own maze. This is basically a way for them to keep the TAs interested so they don't get bored grading the exercise. We don't have any TAs. It's just us folks. So we're just going to skip exercise 4. But you can clearly do it if you want. So exercise 1, the small guy or girl moves. We hope to have a complete game by next week. So the first thing we need to do is create a value player of type picture. That's what this : means. This is of type that, just to remind you. That draws your picture, your figure. So I'm going to be doing this inside Code World as before. Where did we define our other pictures? I believe they're right here. So we're just going to go and add a new value there, a new declaration, player equals, and yes, I am going to line these up because that's how I roll. All right, so for the player, we could draw a little figure. I'm just going to draw a triangle because I'm lazy. And let's make it red. I'm assuming red works. I believe it was solid triangle. Let's look at the documentation. Always a good thing to do. Oh, it's probably solid polygon, I'm guessing. Yeah, it's polygon. Solid polygon, a list of points which makes a picture. Okay, so solid polygon, and then it's a list of points. So we're going to start at, let's see, 0, 0 is the center of the figure, I believe. So we're going to start at negative, I did this once before, negative 0.5. No, because negative is up. 5 and then positive 0.5, I think. Then we're going to go right up to the middle, which is going to be 0.0 and positive 0.5. And then we're going to the lower right, which is going to be positive 0.5, negative 0.5. I think that's right. We'll find out when we go to draw it. All right, so that's our player type. Create a value exercise 1 of type IO that calls interaction of with suitable arguments that the player is drawn on top of the maze, starts in a position where there is ground, cursor keys move the figure around while the maze stays in a fixed position, and the player moves only on tiles of type ground and storage. Trying to move it into any other position will simply leave it in place. So I'm going to say something here about mutability in a little while. And I'm telling you I'm going to say that so that I don't forget it. There's a hint here. Let's come back and read that hint later. Let's just start. I think we already created exercise 1, didn't we? No, we just threw this straight in main. But let's follow the instructions here and actually create an exercise 1. And for right now, we'll just do that. And this was what we did in our last video, episode 5, where we did the prep work for, which was basically the lecture exercise. We did the prep work for this homework. Okay, so the player is drawing. So one thing I do want to call out, if you're doing Haskell for Sokoban, the website, this will already be corrected. But if you're doing the CIS 194 version, as I am, where it says interaction of, that was changed since this was written to activity of. So the first thing, the player is drawn on top of the maze. Well, all of our drawing is handled by this draw world function, which is right here. And it's saying add a coordinate, in coordinate, draw picture of maze. So the question is, where do we want this player to be drawn? Conceptually, I like the idea that picture of maze, the maze itself is not going to move in our final version, right? So I like the idea of leaving picture of maze completely alone. And whatever we're doing with the player, we're going to be drawing at a higher level. So let's go back to draw world. And I'm going to take out why can't I type today? I'm going to take out this in coordinate for right now. We'll get back to it. We'll bring that back later. And I claim that to draw the player on top of the maze, we want to use this ampersand function, which takes two pictures and returns a picture. And I think to draw the player on top of the maze, I think that's all we have to do. Okay, let's see if that works. And we'll also find out if our triangle actually draws. Okay, our triangle is a real mess. I clearly did not think that through correctly. What did I do wrong with that triangle? Right, this makes perfect sense. If I want to start from the lower coordinate, that's negative. Y is negative. I don't know why this is so hard for me. I think in drawing frameworks, I'm used to origin being the corner of what you're drawing, that you're only working in, say, Q1 or quadrant 1 or quadrant 4. And here, we're literally, the origin is the middle of the picture. All right. So we can see now that we actually have a red triangle, boy, that's ugly, on top of our maze. And in fact, if we were to go to Draw World and reverse these, what I would expect is that we would not see the triangle at all because the maze would be drawing over it. Let's see if that's right. Indeed. You can see a little line there. I bet that drawing artifact is where it was. But we'll go back this way. All right, so we're now drawing something on top of the maze. Actually, we're drawing it on top of a box, but who's to say that that's wrong? Me. I'm the one who would say that's wrong. So now that we're drawing something on top of the maze, we need to start it in a position where there is ground, and we can hard code that position. Well, now we're going to bring back this at chord, in chord. Okay. Let's get rid of that. Event handler in chord, and that actually is already there from this initial coordinate, which I think we defined down here as 0, 0, which I think happens to be there. Let's say we wanted to start up in this corner here. Where would that be? That would, well, first let me make sure that I'm right, that is 0, 0 that we're in. I'm pretty sure it is. Okay, so we want to go 3 to the left and 3 up. So let's try that. And then 3 up would be positive. Did we do it? We did, and we're starting in the corner there. Great. All right, what's next? The cursor keys move the figure around while the maze stays in a fixed position. All right, so already I believe that if I use the cursor keys here, it's going to move the whole picture and not just the player. No, it's moving just the player. So what that means is that I misunderstood that this is left associative. So we have an implicit, let's stop it. We have an implicit pair of parentheses around that. We don't need the parentheses to do that. I'm going to put them there because I like things when they are explicit rather than implicit, except in very simple cases. Now, right now, what's driving that movement is our event handler. And we have an event handler which, for the default event, does nothing. And for any key press, moves whatever, changes that returns a new coordinate that is one higher. Okay, now I think I'm going to talk about mutation. There is no mutation happening in this program. And you're not going to see a lot of mutation, certainly in Haskell tutorials, certainly when you're starting to learn Haskell. What we're doing is we're simulating mutation by creating an event loop that takes a value in various functions and then returns a new value, which is different from the previous one. So by mutation, what I mean here is very specifically this von Neumann machine idea that there's, a slot of memory somewhere that holds the value 5, and we're going to poke a new value 6 into it. We're not doing that. We're actually allocating completely new memory and returning a pointer to, essentially, that. That's what we're doing. Anytime you think you see something changing, nothing's changing in some sense. In another sense, we are changing the state by creating a new state, but nothing is changing from the programmer perspective in that von Neumann changing values in cells of memory way. All right, so what do we want to do? Well, we want to handle key presses, and I think the goal here was to use the cursor keys. So we're going to need 4 of these, I think. 1. So let's do we don't need a wild card just for key presses. 2, 3, 4. We've got some warnings here because right now we're duplicating these. So let's go to the Code World documentation, go to events, and look at what the names of the constructors are for the keys. And it's very simple. It's up, down, left, and right, all with capital letters because these are constructors. Okay, so we want up, down, left, and right. And we know that this is already correct. And our creation of various types, in particular the creation of this direction type, is already paying dividends because, that's interesting. Why is that a different color? I wonder if, did I type that wrong? It says up, down, left, right. Maybe I haven't finished this. Let's take a look. Down, left, and right. Well, we're going to have to look at the error. Not in scope. Data constructor up. Perhaps you meant you. Key press up. Key events describe the key as text. This might be that we are not, maybe these types come from the text package rather than from Code World correctly. And in fact, that's what it looks like. Oh, I'm being very silly. These are literally most keys. I didn't even, when you look at the documentation, actually read the documentation, which tells us most keys are represented by a single character text string. So I'm here saying that these are constructors, and they're not. They're strings. So rather than having that up and down, these are literally strings. So this is a great opportunity. Once again, what do I say? You know, there's always the temptation to nuke the mistakes that you make when you're making these videos. And I feel very strongly that you want to show the mistakes, because mistakes are how people learn. And it's very easy to look at the person next to you or virtually next to you and just reach the conclusion that everyone is smarter than you. You're a dope. Why is this so easy for everyone else and so hard for me? And the answer is that it's hard for everyone else. Yes, there are geniuses out there. You know, there's 2 or 3 people who you'll meet in your lifetime who are just naturals at everything. But most of the people you meet struggle just like you do. I used to do a lot of photography, and that's a world where it's very easy to get depressed that other people's photos are so much better than your own. And 999 times out of 1,000, the reason other people's photos are better is that they took 20,000 photos and then only showed you 4. That's why. And so, you know, how do I get to Carnegie Hall? Practice. That's the answer in programming as well. And along the way, you're going to make a lot of mistakes, and you have to embrace the mistakes as how you get better. All right. Sermon over. Having said that, while I'm giving you this little lecture about how these mistakes are making us better, we still have these errors here. So we got to figure that out. So let's look at the error. We could say that it's expecting this internal type for text from data, the data.text package, with an actual type list of characters, list of char. You say char or car? I'd love to know what people do. All right, so this is a Haskellism that you would not know unless someone tells you, or unless you've hit it yourself. So what's going on here is that this bare string is a string. It's a list of characters. If you recall, back in episode 1, I said something about Haskell having terrible string types. We're getting to that. So what you might want to do is you might want to explicitly, assuming we had access to the data text package, you might want to explicitly create this as a text string. And you might do that like this. But that's actually not going to work. And the reason that's not going to work, other than the obvious syntax error that I've got there, is that this is a pattern. So if I wanted to do this way, this explicit conversion, I would need to use something other than pattern matching here. I would probably use essentially a switch, a case statement to do this. But you know me, I just love pattern matching. So I would rather keep using pattern matching. So I'm going to show you something that almost every Haskell program you see in the wild will have, which is this. A language directive, overloaded strings, and hopefully I'm getting the capitalization correct here. All right, and now I'm going to remove that. Good. So what we just did here is we had a conversation with the compiler, and that conversation went a little bit like this. Look, Haskell, you have a problem. I'm your friend. I've known you for years. And this thing with the strings, it's got to stop. You can't keep making programmers explicitly convert from string to text and from text to string and to byte string. You're driving everyone around you mad. From now on, just take any string and treat it as any of these data types. Would you please? That's what overloaded strings means. And now, thanks to that, we can just use these bare strings here. And they will be treated as the appropriate type, whether that is a list of char or whether that is a data text. All right, a lot of talking. Let's see if it works. Compiling. Good. And there we are moving around. We can go out of bounds. We can do all sorts of stuff. Fantastic. The player moves only on tiles of type ground and storage. Trying to move it into any other position will simply leave it in place. All right. So right now, we have these event handlers. Let me stop this so that we can actually read. These event handlers are just calling a JSON chord. And I think we use a JSON chord for a few other things, don't we? Right now we're only using it for this, but I could easily imagine wanting to use this for something else. So I don't want to place that logic too low. I want my kind of business logic to be somewhere a little bit higher. All right, let's make a new function. We'll call it try_move. And try_move is going to take an initial coordinate, a direction. Is direction what I called that? I hope so. It is. Good. You know what? I'm getting tired of this. These data types, darn it, data types should go up near the top of your program. I'm going to put them there. So it's going to take a coordinate, a direction, and it's going to return a coordinate. So if we're doing that, right, in coord and a direction, I think we can do this. This is actually a good place for a simple conditional. So if this coordinate is equal to, what do we say? Storage or ground, right? Storage or ground. So we could do this and then have a complex if statement, but I'd rather simplify this. So let's make a new one, a new function, which is going to be of type tile. And it's going to return a Boolean. I think it's bool. Is it bool or Boolean? I guess it's Boolean. Once again, I'm using pattern matching because I love it. Everything else is going to be false, right? Why doesn't it like that? Parse error. Oh, that's just because we're not doing here. Okay, so now let's get rid of this, what we were about to start doing. Yeah. Then let's see, can you guess what I'm going to do after I finish this function and get it working? Okay, that should work. However, I'm clearly, okay, it was bool. I had a 50-50 chance of getting that right, and I got it wrong. Oh, and this needs a tile rather than a coordinate. So I think we need, that's picture of, no, a maze takes an integer. Now I think we want to look at that hint. It might yield nicer code to change the type of maze to coord to tile. Do not hesitate to make that change. Well, guess what? I'm going to do that right now. So rather than integer to integer, we're going to change this to coord. We get to see what refactoring in Haskell looks like. It's actually as simple as that. Being able to decompose this type in a pattern is just very, very simple. We literally changed almost nothing. All right. So now, coming back to up here, can move to. Right. Yes. We've got some nested parentheses going on here. This might be where if you didn't like the parentheses, you could start doing things this way. And in fact, we could even do that. This is super confusing the first few times you do it. Again, space is the function application operator, and $ is also a function application operator, but it binds less strongly in terms of basically where the parentheses are going here. We have implicit parentheses because we used these $. We've changed the associativity of this expression. All right, so I said before I even try this, I got to do it. I'm using something twice, and so I would rather make this neater. So if we can move to this new coordinate in the maze, where new coordinate is this sub-expression, then do it. Let's see if it works. Okay, we've got a problem here, and this is because we changed the type of maze, but did not change the call site of it, I believe. Yep. And so once again, this is a very simple mechanical transformation. Did I get everything? All the calls to maze? Let's see. Looks like we did. All right, we can move around. That is a box. I was able to move on it. All right, whatever I did not work. Am I not calling this function? Maybe I forgot. Maybe I wrote this try move function and yeah, I wrote this function and then never actually used it. Oops. So we are going to adjust our event handlers, and they're going to look like this. Try move from our in coordinate with some direction. Right, like that. That's down, that's left, and that's right. Yeah. Try it again. Cannot move onto the box, that's good. Cannot move onto the wall. I can move into the storage. Great, so we've done, I think that's exercise 1, right? Yeah, congratulations. We have now finished exercise 1 of homework 2. I'm going to cut the video here, and when we come back, we will do exercise 2 of homework 2, getting closer to Sokoban.